Chapter 2, Section 5, Implicit Differentiation. Now, most everything that we've looked at when we've been looking to take the derivative of, or in some cases even solving, as far as for graphing and such, has been equations or functions that have been written in what we call explicit form, where the variable y is written in terms of x, as I have some examples right here. The y is all by itself on one side, and everything on the other side is in terms of x. Now, sometimes, well, we're not that fortunate. It's not easy to take an equation and rewrite it in such a manner that we can isolate the y. This last example over here, in fact, if you multiplied both sides by x, assuming that x can't be 0, I would get xy is equal to 1. When you have it such that the x and the y's are kind of like mixed in together, where the y is not isolated, then what we have is what we say is written in implicit form. A function is implicit form. Normally what we try to do is we try to rewrite it into explicit form. If I was given this, I probably wouldn't work with this. I'd rewrite it and solve for y. But they're not always that simple. Sometimes it's easy to do, sometimes it's not so easy to do. When we can't easily isolate the y, but we still want to find the derivative, then we use implicit, because of the form of the equations written in, implicit differentiation, which is involving the chain rule. The most important part, the key to implicit differentiation is to remember that the differentiation is taking place with respect to x, whatever the independent variable. It might be x, it might be t. So what we want to do is when we take the derivatives that have terms that have just the x or just the t, we take the derivatives of those and differentiate as we always have. But when we have terms that involve y, then we have to use the chain rule, because we have to think of y as a function of x, a differentiable function of x. Here, for example, I'm asking you to take the derivative with respect to x of y to the 5th power. So we have to think of y as a differentiable function of x, like it was 2x squared plus 3, or the sine of x. So we would use the chain rule, because first we would do it with respect to the outer. This is my inner function with respect to the outer function, so that would be 5y to the 4th power, subtract 1 from the exponent, but then we'd have to multiply it times the derivative of y with respect to x, which we would just write as dy dx. Some people write the y prime. That's okay. Just be careful, because if you have a really messy expression, all of a sudden y prime start to look like y to the 1st or something like that. But either way, I prefer to use Leibniz notation. This next example is asking you to do the same thing, and I've got y here, but what I want to have to approach this with is the idea that it is a product of two functions, of x to the 4th and y to the 3rd. So I have to use the product rule. So it's the first one times the derivative of the second one. Now, the derivative of y to the 3rd, I kind of do it like I just did the derivative of y to the 5th. This would be 3y to the 2nd power times dy dx. You can see the little chain rule part right here. Plus the second one times the derivative of the first one, which is 4x to the 3rd. Because this first term, it just has x, when I take the derivative of it, I take the derivative as I have been doing in the past three sections, and I just use those rules. Now, if you wanted to think of it as, dx dx, well, dx over dx is kind of like 1, so that's why it's not written down. Now, I wouldn't probably leave my final answer in this form, neaten it up a little bit, maybe write this as 3x to the 4th, y to the 2nd, dy dx, plus 4x to the 3rd, y to the 3rd. That looks a little bit neater and a little less complicated. Now, in this next problem, I have a regular equation instead of just an expression, and I want to find dy dx. So I'm going to first do implicit differentiation, and then I'm going to solve for dy dx. So the derivative of x to the 3rd is 3x to the 2nd. That part's not so bad. Plus the derivative of y squared. It's kind of like how I took the derivative of y to the 5th. It's a generalized power rule, so it's 2y to the 1st times dy dx. There's the chain rule. Plus the derivative of 5y. Well, the derivative of 5y is 5 times the derivative of y, which would be dy dx. And of course the derivative of 0 is 0. Now I'm not done because it says find dy dx. So I'm going to subtract 3x squared from both sides. It's the only term over here that doesn't have a dy dx. And I'm going to factor the dy dx here out of these two terms. So I'm going to kind of do two steps. I'm going to write 2y plus 5 times dy dx is equal to negative 3x squared. And now I'm just going to divide and write dy dx is equal to negative 3x squared all over the quantity 2y plus 5. And I have differentiated implicitly. It's a little different. I don't think it's that bad. It's just like about any new lesson that you're going to see. It just takes a little bit of practice to get used to it. Here are my guidelines. I've got all written out nicely for you. Differentiate both sides of the equation with respect to x. Collect all the terms with dy dx. That's an x there, although you can't hardly see it. On the left side of the equation, move all the other terms to the right or vice versa. Factor the dy dx out of the left side, and then solve for dy dx by dividing both sides. So I'm going to do that on these next couple of examples here as well. So find dy dx, it's written implicitly. This would be 2 times y to the first power dy dx plus the derivative of 5y, that's 5 times the derivative of y, which is dy dx, minus the derivative of 7x to the fourth is just straightforward because it's all in terms of x, 28x to the third, and the derivative of 9, the derivative of constant, 0. So these two terms stay, and I'm going to factor out the dy dx. But I'm going to add 28x to the third to both sides. Now I'm going to divide and get the dy dx all by itself, and I get 28x to the third dividing by 2y plus 5 all over 2y plus 5. Oh, this one looks like a fun one. Throw in some trig. The derivative of the sine of x squared y. This is my inside function, and it's a product, and it involves y. So I have to be very careful. Take the derivative of the outside function times the derivative of the inside function. Product rule, so it's the first one times the derivative of the second, the derivative of y is dy dx, plus the second one times the derivative of the first part, which is just 2x, all right, minus the derivative of 4 cosine x would be plus, because it's minus the opposite, would be plus 4 sine x equals 0. I have to get the dy dx by itself, so what I'm going to do, and it's going to look a little messy, is I'm going to actually distribute through by the cosine of x squared y. So I have x squared times the cosine of x squared y dy dx, that's the first part, this times this, plus I'm going to write the 2xy times the cosine of x squared y, and then I'm going to go ahead, because I might as well, I'll just go ahead and do it in the next step, plus 4 sine x equals 0. So these two guys go over here. I subtract, and I'm going to have to divide. I have x squared cosine of x squared y dy dx equals negative 2xy cosine of x squared y minus 4 sine of x. Now I'm going to divide both sides by x squared cosine of x squared y, that quantity. Really getting messy here. And in fact, I'll just bring it right. Well, maybe I can squeeze her in. So I have dy dx is equal to all of this over the. Now you could factor out a negative 2 if you wanted to, but nothing cancels top and bottom. So I'm just going to leave it as is. Negative 2xy cosine of x squared y minus 4. That's a minus sign there. Minus 4 sine of x all over x squared cosine of x squared y. All right, you don't want to have the TV on when you're doing these and be distracted, because it'd be easy to lose a sign or lose a factor or even a term. Next guy up, find the slope of the circle. Oh, neat. X squared plus y squared equals 25 at the point 3, negative 4. Well, to find the slope of the circle means to find the slope of the tangent line of the circle at this point. So I differentiate. I get 2x plus, derivative here is 2y to the first times dy dx equals 0. Derivative of 25 is 0. If I subtract 2x, I get 2y dy dx is equal to negative 2x, and then divide by 2y, I get dy dx is equal to the opposite of x over y. Now in this case, to find the slope, we take the derivative and then we plug in, but I'm not just plugging in for x because both variables are in here. So the 3 goes in for the x, the negative 4 goes in for the y. So dy dx at the point 3, negative 4 is equal to the opposite of 3 over negative 4, which is 3/4. And there's my slope. Find the slope of this graph at the point 3, 1. Very similar. I don't know if I left myself enough space here. I hope I did. So take the derivative here. I definitely have a generalized power rule here. I'm going to bring the 2 in front. That's going to give me 6 times x squared plus y squared to the first power times the derivative of the inside function, which would be 2x plus 2y times dy dx, we'll chain rule there, equals, and on this side, it's a product rule. I think of this as 100x and y as my two functions. The first one times the derivative of the second, derivative of y is dy dx, plus the second one times the derivative of the first, which should be 100. Now, it would take a little bit to get dy dx all by itself on one side, as the guidelines for implicit differentiation tell you to do. But that's because we can avoid that because they're not wanting dy dx. They want to know what the slope is at the point 3, 1. So let's just plug 3 and 1 in, and all this stuff is going to simplify, I think, a little bit more nicely. 6 times 3 squared plus 1 squared times 2 times 3 plus 2 times 1 times dy dx is equal to 100 times 3 times dy dx plus 1 times 100. So everywhere I saw an x, I plugged in a 3, and everywhere I saw a y, I plugged in a 1. This is 10 times 6. This is 60 times, this would be, that's a 2 there, that'd be 6 plus 2 dy dx is equal to 300 dy dx plus 100. So I distribute, I get 360 plus 120 dy dx is equal to 300 dy dx plus 100. I'm going to subtract 120 dy dx from both sides and subtract 100 from both sides. I get 260 equals 180 dy dx. I'm almost out of space here. Divide by 180, and I get dy dx is equal to 260 over 180, 26 over 18, it'd be 13/9. So that's your slope, 13/9. I'd still be working on this problem if I was trying to isolate dy dx. And just when you thought it was safe to go back into the water, comes the newest sequel of Jaws. Here we're going to try to find the second derivative implicitly. So what we're going to do first is take the first derivative, because we know to find the second derivative, you take the derivative of the first derivative. This is going to be 6x squared minus, this would be 6y times dy dx equals 0. Now before I go any further, I'm going to kind of figure out what's going on here with dy dx. I can subtract 6x squared and then divide by negative 6y, and I get dy dx is equal to x squared over y. That's the first derivative. Now to find the second derivative, I'm going to have to use the quotient rule. So the second derivative is equal to low d high minus high d low, the derivative of y is dy dx, over the square of what's below. Now I got a problem, several, but I have a problem here. The second derivative of y with respect to x is in terms of x, y, and the first derivative. I can't have this first derivative here. If I only knew what the first derivative was, then perhaps I could substitute in for it, and that's exactly what I'm going to do. So my second derivative is equal to 2xy minus x squared times x squared over y all over y squared. Now I'm not too crazy about having this y here, so I'll multiply top and bottom by y, and I get 2xy squared. The y's cancel here, so it's going to give me minus x to the fourth all over y to the third. Now you could factor an x out of the top, but nothing's going to cancel, so I think I'm good here. The trick to this, take the first derivative, solve for dy dx, take the second derivative, and then make your substitution because the first derivative is going to be part of the second derivative. Now, before I let this section completely get away from me here, I wanted to make mention of the idea of a normal line. Find the equation of the tangent line and the normal line of the circle, or to the circle at the indicated point 4,3. It's x squared plus y squared equals 25. The derivative is going to be nice and easy. So what does it mean about the normal line? Well, we know what it means with a tangent line, so we need the derivative. So let's start off by using that. This is 2x plus 2y to the first times dy dx is equal to 0. So that means 2y times dy dx is equal to negative 2x. That means dy dx is equal, divide both sides by 2y, the opposite of x over y. Now to find the equation of the tangent line, I'm going to plug 4,3 in. So that means that dy dx at the point 4,3 is equal to the opposite of 4 over 3, or negative 4/3. This is the slope of the tangent line. Okay, so we have a circle. We have 4,3 over here, and we just found the slope of that line. The normal line is the line that goes through the point of tangency and also through the center. So that means it's perpendicular. And if it's perpendicular to the tangent line, the slope of the normal line would be the opposite reciprocal over 3/4. So we can find that as well. Now we have the point here, 4,3, and it's the same point down here, 4,3. So y minus 3 equals negative 4/3 times x minus 4. Down here, y minus 3 equals positive 3/4 times x minus 4. So this is the tangent line, and this is the normal line. So if you see that expression, it means perpendicular to at the point of tangency to the tangent line. Now they don't talk about normal vectors that are perpendicular. They talk about orthogonal vectors. And so depending on what you're working with, lines, vectors, and such, determines what your adjective is. All right. Implicit differentiation is always on the AP. Of course, it's going to be, in the assignment and on the test. So make sure that you practice, practice, practice.